There's number 2. If your answer is not exactly like mine, it's okay. It should be close to 2F, but it doesn't have to be exactly the same. Speaking of which, don't forget on Monday we have a quiz. On the quiz, there's going to be 7 multiple choice questions and 2 ray diagrams. So if I were grading this on the quiz, first of all, I'd get 100%. I did it right. Let me show you what I'm going to grade you on so you know. I will first of all check to make sure that you have the location of the image correct. So it's right here. Secondly, you've got to draw the image correctly. I sometimes have students who just draw an arrow pointing to this spot like, hey, this is where the image is, right here. But they don't actually draw the image in. I'll also make sure you have real lines where they should be real, and like on number 4, dashed lines where they should be dashed. And then the last thing I'm going to check for is to make sure you have the arrows showing what happens to the light. I want to know that you know this is not some sort of fancy pattern like geometry, but this is describing what happens with real light. It comes in here and it bounces down there and whatever it does. I can, yes. Number 3, like this, and there's number 4 as well. Backside number 5. Your picture may not be exactly the same as mine because you got to choose where you put the object. I put my object here. If you put your object farther away, like somewhere in this region, then your image would be closer to the focal point, it'd be somewhere over here. Definitely smaller. If you put your object closer to the mirror, like right here, then your image would be closer to the mirror and it'd be definitely bigger than mine. But still smaller than the object. Frank?
So for a convex mirror, you never get that invisible spot, so the focal point's behind it.
Yes, well done. You never get the invisible spot. I can't say it better.
Vampire spot.
Vampire spot, yes, okay, we can call it that. You know how vampires can't see themselves in mirrors?
They're always in the focal point.
Yeah, my theory is they're always at the focal point of a concave mirror. That's right.
It's just a big coincidence.
Yeah, right, every time.
What about a flat mirror?
I don't believe in vampires. I don't like the word believe anyway. I don't think vampires are real. Well, and I don't think aliens are real either. But
Oh, that's false.
They are real.
oh my goodness.
What if vampires look into a flat mirror?
Yeah, you're missing the joke.
I didn't know it was a joke.
Well, it was funny, and that was supposed to indicate that it was a joke.
Oh, I was confused because nobody laughed.
Oh.
Are we getting this on video?
That's good. Yeah. Cut all of that part out.
No.
That was a good discussion.
Down below,
Every time I speak, it's just going to be
Now-
cut out.
Oh, you wanted us
your image position, I actually measured them. I don't care if you do. Here's what I was thinking. In this area, you might put like between F and 2F. Or maybe you put greater than F, less than 2F. That's fine. This one should be exactly 2F. This one should be greater than 2F. We'll talk about this one in a minute. Actually, we talked about it yesterday too. And then this last one, maybe you put behind the mirror. That's okay with me.
Negative.
Or negative DI. That's fine too. Then for the others, you got inverted, inverted, inverted. Leave the other one blank, and then upright. For magnification, we got smaller, same, larger. Blank, we'll talk about in a second, and larger. And then over here, we got real, real, real. Blank, and the last one is virtual. Down below, the image position is always, for convex mirrors, it is always behind the mirror. It's always upright, always smaller, and always virtual. Yesterday we talked about this one. Actually, Christine asked this question. Are you okay with me moving on, or do you not remember it?
I don't remember.
Don't remember it, okay. I'll show you real quick. So let's say we've got an object at the focal point. So I'm going to draw a smiley face right here. And I'm going to put fangs. It's a vampire. Which, by the way, I don't think that they exist. Just so we're clear on that. Rajiv. Pranav. Oh my goodness, Rajiv is like 4 or 5 years ago. That's embarrassing.
We get a video? Yes, we have video. We're taking video right now. I hope you can.
I found that one.
They got that on video.
Sorry.
Red?
Sorry, Pranav. I'm so.
I don't know. I kind of want to.
It's a good day.
Good job. My plan of the day really consists of getting
I-
the packers and not going to Starbucks. Probably lower to
Is that racist?
Going to Starbucks? Really everywhere.
One time I met an old friend from high school and I called him the wrong name. It's awful.
You just called them the wrong name.
Oh, 5, yeah.
I know, but that was an old friend from high school. It's even worse when it's an old friend from high school.
Mixed up and then
I went up to the old friend from high school and said, "Hey, Tony, what's going on?"
And they're just like, I'm not doing
And my brother, who was with me, punched me and he was, his name was Mark.
No. Yeah.
He was at a wedding.
Maybe we should change the smiley face.
One
to
thing
a
is
brown
so
face.
awkward.
Okay, come on in, have a seat, join us. We were just talking about awkward moments.
You're not in
And
our
you guys
class.
walked in. Yeah, that was fine.
Here, Becky, it's right here. I said that wasn't
So,
So here's how you find the image for this one. Just like we've done before. One very easy raise from the top
Red, stop it.
of the object. And it goes to hit the mirror. After it hits the mirror, Red, where does that reflect? Any parallel ray?
Any parallel ray will go back to the focal point.
Yes, back to the focal point. So that looks like this. The second easy ray is one that goes through the focal point and then hits, but this one doesn't hit the mirror.
Ah,
Way to go through the focal point.
Yeah, there's always one that goes through the focal point, hits the mirror, and then bounces out parallel to the principal axis. But this one doesn't hit the mirror, so I can't use that easy ray.
yeah, it doesn't. The image doesn't exist. What?
The second easy, the first easy ray,
I got that.
parallel through the focal point. The second easy ray is through the focal point, hits the mirror, and comes out parallel. But I can't do that this time. So I've got to go to my third easy ray. What's the third easy ray?
That's like.
What's that, Frank?
Lucy off the top.
Very good. Yeah, any ray that comes from the center of curvature hits the mirror, and well, I'll just pretend the mirror keeps going here. And it goes right back to where it came from, something like this. Now remember, we have to look at what your eye sees. Your eye sees this ray, and your eye sees this ray. Those rays cross.
No, they're parallel.
No, they never do. In fact, even if I extend it back, which is always, if you can't figure it out, you should always extend the rays. Which rays do we extend? The reflected rays or the incident rays?
Reflected.
Reflected rays, very good. That's important for the quiz on Monday. If I extend those reflected rays back, they never cross. And so you get no image. And that's what you should have on this part of the chart then. You can just write in there, no image, doesn't exist.
Is C the same as 2F?
Yes, the center of curvature is 2 times the focal length.
Okay.
Yes. So I have a headlight here. This is a headlight from a car at the headlight store. And take a look at the back of this thing. What does that look like?
Concave mirror.
That's a curved mirror. In fact, it's parabolic. It's a parabola. Okay, so it's a curved mirror. And on a headlight, you want the beams of light, the rays of light to come out of this thing parallel to each other so it can shoot way down the road and see far, far away. How do I get the rays of light to be parallel? Where do I put the light bulb inside of a concave mirror to make sure the rays of light come out parallel? Yes, facing that way, but I can be more specific than that. Nate?
Focus.
Yeah, if I put it right in the focal point, then they bounce off of the mirror and all come out parallel to each other.
Would they not exist? Focal way?
Well, there's no image, there would be no image of it,
Wait, is that the?
but the rays would all come out parallel to each other. It's just like, you ever see, like with a grand opening of a store, they have these big searchlights outside, and they shoot beams of light, and all those, the beams of light are all parallel. Same thing, they have a big mirror, a huge mirror, put a really strong light bulb at the focal point of the curved mirror, and then all the rays come out parallel to each other. Physics, you can't get away from it. I'm going to pass around this little demonstration, and then we'll get to our notes for today. In this I have a concave mirror here, and I have another concave mirror. This one just has a hole in it. I'm going to put an object in here. Okay. And then I'm going to put this on top, and as you know with concave mirrors, they can form real images. So as this comes around, you'll see the real image. And it will look like you can grab this. It's so real. Because it's a real image, it'll look like you can grab it. You can't really. It looks like it. This thing is called a mirage because of that. And later in the period, if we have time, I'll put a little flame in there. And it looks like you can grab the flame because it's a real image of flame. But you're actually not touching the flame. Okay, now notes. You need to have a piece of paper out for notes.
It's not there, Eric. You can't touch it.
All right. Time to talk about equations. We haven't had any equations in this unit, and we're already the 5th day in. I feel like we should have equations. So the last couple of days, you've been finding locations of images by using ray diagrams. You can find locations of images with equations too. So that's what I'm going to teach today. It shouldn't take too long because most of the equations are just plug and chug. Here's the equation, the first one. 1 over f equals 1 over d o plus 1 over di.
Are these all distances?
Yes, they are. Good question. These are all lengths of some kind, measured in meters or centimeters. In this equation, what does the f stand for? Be careful, not focal point, but close. The focal length. The f is my focal length. DO stands for? Yeah, distance of the object, or distance to the object. What does DI stand for?
Distance to the image.
Distance to the image. Very good. To put that all in picture form, let's take a look at an object like this. What kind of mirror is that? That's a concave mirror. Very good.
Mr. English,
Yes.
wouldn't you have to specify that it's a concave parabolic mirror instead of a spherical mirror?
Good question. In our class, we're going to treat them the same way.
Okay.
They're not the same, but close enough. In this picture then, you'd have this length right here is your focal length. We always measure to the mirror. This length from the object to the mirror is DO. Again, we're always measuring to the mirror. And if I drew my ray diagram, just like you did on your home learning, you would see that the image is somewhere over here. And so then at the end, that's my DI, image distance. So it's important to know that on the front of the mirror, all those distances are going to be called positive distances. Behind the mirror, all those distances will be negative distances. In front of the mirror, positive distances. Behind the mirror, negative distances. So in the picture I've drawn here, all of those distances, F, DO, and DI, are all positive. What kind of image has a negative DI? Behind the mirror, what do we call those images?
Virtual.
Those are virtual images, right? So if we have an image that's over here, and your home learning was number 4, you have an image behind the mirror that's a virtual image and it's a negative DI in that case. Okay, if I did this for convex mirrors, it looks something like this. Here's my focal point, and I have my object right there. Again, we always measure to the mirror. So that's DO. For convex, I have a negative focal length because it's always behind the mirror. And my image in this case would be somewhere in here. And I have a negative DI then because it's behind the mirror. The signs are the same exact as for concave. The front of the mirror is positive, behind the mirror is negative.
Wouldn't the O be negative then? Because aren't you measuring it from the focal point?
No, you always measure from the mirror.
From the image of the mirror?
Image to the mirror, focal point to the mirror, everything goes back to the mirror. DO is positive because that's on the front of the mirror.
Okay.
Everything in front of the mirror, on both cases, it's the exact same thing. Everything in front of the mirror is positive distance. Everything behind the mirror is negative distance for both. It's just like a number line. It won't be that easy with lenses, but for mirrors, it's that easy. Now this equation shows up so much, it's really kind of annoying to always say 1 over F equals 1 over DO plus 1 over DI. So from now on, we're just going to call this the if I do I die equation. We're all on the same page. That means if I do I die. That's the equation name. Okay. There is one more equation you need to know about curved mirrors. It looks like this. In this equation, the h stands for what?
Height.
Height, very good. So I've got height of the image divided by height of the object equals negative di over do. Same as before, object distance and image distance. So this is just telling you the ratio of the distances is the same as the ratio of the heights. Tells you how much is magnified. Now, if you do some number crunching on this, you can see that you could end up with a negative h. What does it mean if you have a negative height for an image or a negative height for an object? Carolina?
It's inverted.
Yeah, it's inverted. Very good. So just like before, the negative and positive in physics still means the direction. In this case, it's the direction of the image. Is it upside down or is it right side up? Okay. If I went too fast for you, I'm going to put this on my website so AP people can see this that missed today. I also just remembered this right now. I think Mrs. Giggler, or maybe she just found this on YouTube, I'm not sure. She has on her website, and I'll post a link on my website, to how to draw flat mirror ray diagrams, if you want to see those. The quiz on Monday has 2 ray diagrams you have to do, and has 7 multiple choice questions. On Monday, so I'm giving you, what, 25 minutes to work on home learning now? Yeah, that's a lot. So on Monday, I'll go over 1 question as a class, and then we'll take our quiz. You probably can finish today's home learning in class. So if you haven't grabbed one of these, come grab it. Feel free to move around the room, work with each other. The answers are on the back. The whole thing is due on Monday.